ICAO report on feasibility of a long-term aspirational goal for international civil aviation CO2 emission reductions, LTAG. Introduction to the ICAO LTAG process. Good morning, or good afternoon, or good evening. It is a pleasure to present to you this important report on the feasibility of a long-term aspirational goal for international aviation CO2 emission reductions. To simplify things, I will refer to that long term as LTAG. This report was approved by consensus at the recently held CAPE 12 meeting. CAPE recommended that it be used as the basis for further consideration of this LTAG. The LTAG final report was also made publicly available on the ICAO website. This is an unprecedented effort in CAPE that involved more than 200 of the best experts in that area from all regions of the world. It is robust, it is balanced, it is factual, and it focuses on in-sector CO2 emission reductions. It is a pleasure, then, to start. Now we will move on to present the overview of the CAPE report, exploring the feasibility of a long-term aspirational goal for which, as you have seen, many people spent a lot of time working in order to come to the result that we are going to see here. The ICAO LTAG process. This slide gives an overarching description of the ICAO CAPE LTAG process, which was and is conducted in an open, transparent, and inclusive manner. I should underline here, the process is focused on in-sector measures and includes considerations of all the innovations available. You can see how we structured this work on the right-hand side of the slide. We had a subgroup working on operations, looking at air operations and operations on the ground, how they could be improved in the future. We looked at the technology side from alternative energy sources to developments in airframe and propulsion, but also what new and advanced concepts could bring towards 2050 and even up to 2070. But in particular, we also had a very close look into fuels. On one side, drop-in fuels, cryogenic fuels, electricity-based fuels, but also in the sources of energy, where the energy to produce such fuels could possibly come from, and what this would mean to the whole process. We also had a look into issues related to transport and storage, in particular of new sources of energy for new fuels. All this work was then combined in 3 scenarios, which also looked at the timing of when certain developments might find their way into daily life, meaning the readiness attainability of certain goals. And then, of course, the most important part, in conclusion, we looked at the related CO2 reductions that could be achieved with all this. So, a very complex process, but we managed to compile it into a comprehensive report. ICAO LTAG work general timeline. This is a slide you have already seen. I would like to present it once again here just to re-emphasize that a lot of work has been undertaken in a very short amount of time. Excellent cooperation around the globe with many people from science and technology, and with an excellent support also from the Secretariat, organizing many meetings which provided a lot of insight into what might be coming along in the near and far future. So where are we now after 2 years and 2 months of working? CAPE has completed the technical work, and the CAPE 12 meeting agreed to recommend for Council consideration the final report, providing the results of the technical work, which explores the feasibility of such a long-term aspirational goal. I would like to underline it here one more time. This recommendation from CAPE was decided unanimously, so it was very clear that the whole of CAPE stands behind this work, and it was also important that CAPE noted that no further work would be needed in this area because this would not bring fundamentally new insights or new results that would go beyond what has been evaluated already. This final report was made available on the ICAO website. ICAO traffic demand forecast. So how does this all fit together? Of course, Cape knew that we are living in the real world and that we cannot just invent any fantastic thoughts of how nice and bright things might look in the future. No, all the work was based on a long-term traffic forecast on various fit scenarios that were developed by ICAO. This work already incorporates the near and long-term effects of the COVID-19 pandemic, and I think it's very important to note that what has been used data-wise is exactly the same input material that CAPE also used for its environmental trends work. In addition, I should mention here that in the ICAO environmental trends work, the forecast usually reaches out to 2050, but for the LTAG work it was extended to 2070 to take into account certain effects of developments that will enter into service only very close to 2050, which we have been mainly looking at, but just to show how things might develop. We were looking actually beyond 2050. There was an extrapolation out to 2070. Hi, beautiful. LTAG fleet evolution. What did we do in terms of the fleet evolution? I already mentioned that all the input assumptions were the same as we use for the ICAO environmental trends, so there's consistency there. Also, the fleet evolution output exactly matches the trends through 2050, and everything is consistent with the projections from the ICAO Aviation Data Analysis Panel, ADAP, so everything goes hand in hand. We have then also extrapolated fleet evolution data out to 2070, and we introduced into the modeling some advanced tube and wing technology improvements and advanced concept aircraft to complete the whole picture. Then the outputs generated by the modeling were expressed in results for the years 2040, 2050, 2060, and 2070, and they are available in terms of available seat kilometers, available ton kilometers, operations, and in-service fleet by age. LTAG modeling and future years processing. How did the modeling process go? We took a base year and added future operations to that. In order to be able to do that, we took baseline assumptions, which were all the same for all these scenarios we developed. Then we added several levels of technology improvements, operational improvements, and alternative fuels. Operational and fuel improvements and alternative fuels were added to all scenarios and technology improvements, stepwise. We then calculated the results with various greenhouse gas models and came then to the LTAG scenario-based results, which we will see a little later in this presentation. Scientific input based on IPCC 2021 Assessment Report 6. So the last step here that I would like to mention is on an important task undertaken by CAPE, as well as to align all of the results with the latest scientific ones. For that, we referred to the IPCC results published in its Assessment Report 6 in 2021. As a basis, we assumed that for warming of 1.5 degrees Celsius, global warming, the allowed cumulative global anthropogenic CO2 emissions from 2020 onwards would be 400 gigatons of CO2 at 67% probability, and 500 gigatons at 50% probability, and for a warming of 2 degrees Celsius, the allowed cumulative emissions would be at the level of 1,150 gigatons of CO2 at 67% probability and 1,350 gigatons at 50% probability. But it's important to note here that the uncertainty on these estimates is largely due to a range of physical factors, including non-CO2 effects from other greenhouse gases, such as methane, nitrous oxides, and fluorinated gases. Allowed emissions for limiting global mean temperature increase. This slide shows on the left-hand side the various scenarios taken from the IPCC Assessment Report 6 from its Working Group 1 in 2021, which show the different scenarios, the different available tons of CO2 that could be emitted, and what the result might be looking out to 2050 and the year 2100. And just to inform you, CAPE used the very low emission scenario as indicated here by a light blue line, and the low and very low emission scenarios indicated here with a dark blue line. These are the only 2 scenarios which would allow for reaching the goals that have been agreed on under the Paris Agreement. Introduction to the ICAO LTAG report. Now moving on to the final ICAO report that explores the feasibility of a long-term aspirational goal for international aviation CO2 emission reductions. The structure. This part of the presentation consists of 5 sections. First, we will have an overview of LTAG work. Then we will focus on the 4 elements of LTAG work: the LTAG scenario development, the LTAG technology, the LTAG operations, and last but not least, LTAG fuels. Overview of LTAG TG work. I would like to start with the overview of LTAG work. Methodology overview. First, I would like to describe the methodology used for the LTAG TG feasibility study. We started with data gathering. This process embraced aircraft technologies, operations, and fuels areas, which contributed to each element of the integrated scenarios. On the economic modeling and traffic forecast, the fleet evolution was evaluated, which was fed into the CO2 emissions modeling. Additionally, the consensus scientific knowledge on climate change was the basis for putting the analysis outputs into this context, as explained in previous slides. And the results listed on the right column will be presented to you later today: CO2 emissions trends, cost estimations, and additional analysis, including a sensitivity analysis application in context of scientific knowledge. Methodology integrated scenario. To go a little deeper on the methodology, a set of integrated scenarios was built. The baseline scenario was numbered as 0, and then 3 other scenarios were developed to represent the level of efforts and aspirations associated with the degrees of readiness and attainability. These were numbered from 1 to 3. The integrated scenario 1 represents the pathway with highest readiness level and attainability, but with the lowest aspiration, while integrated scenario 3 offers highest aspiration, but requires greater efforts to be attained. The integrated scenario 2 is a middle path between scenarios 1 and 3. Key questions addressed. This slide shows key questions to be addressed by the LTAG-TG and reflected in the corresponding sections of the CAPE report, referenced on the right side. These questions are: Question 1. How could in-sector measures help reduce CO2 emissions from international aviation through 2050 and beyond? Question 2. Given CO2 emissions trends for each scenario, what would be the cumulative emissions from aviation? How do cumulative aviation emissions compare to requirements to limit the global temperature increase to 1.5 degrees Celsius and 2 degrees Celsius? Question 3. What investments are required to support the implementation of the in-sector measures associated with each scenario? What would be the cost impacts to aviation stakeholders? Question 4. What would be the impacts of various future aviation traffic levels? Question 5. How sensitive are the results to scenario assumptions? Reductions in CO2 emissions from international aviation through in-sector measures through 2050 and beyond. On the first question, this slide provides a concise overview of the reductions in CO2 emissions from international aviation through in-sector measures through 2050 and beyond. This is a key takeaway from the entire report. The presentation today will describe the technical work carried out to get to this input. In terms of CO2 emissions in 2050, after the implemented measures, the CO2 emissions range from 950 megatons of CO2 for IS-1 to 200 megatons of CO2 for IS-3, which is around 35% of the 2019 CO2 emissions level. The contribution of the CO2 emissions reduction measures varies from 39% to 87%. In terms of a breakdown, the fuels part is the biggest with a range of 15% to 55%, followed by the technology with around 20% share, and with operations ranging from 4% to 11%. And for your reference, the cumulative residual CO2 emissions from 2020 to 2070 are also provided at the bottom in the table. CO2 emissions reductions, high-level observations. With regard to the high-level observations, I would like to draw your attention to the following general points. Scenarios show the potential for substantial CO2 reduction. However, none of them reach zero CO2 emissions using in-sector measures only. There will be residual emissions despite 100% replacement of conventional jet fuel with novel fuels due to consideration of fuel's life cycle emissions. As other aspects of economies reduce their emissions, the life cycle value should drop as well. Out-of-sector measures were not considered in the LTAG analysis, only in-sector measures were analyzed. On the technology side, advanced tube and wing aircraft have a clear potential to improve the fuel and energy efficiency of the international aviation system, with some incremental contribution from aircraft with unconventional configurations. The technology wedge continues to grow after 2050 as these aircraft penetrate the fleet. Hydrogen-powered aircraft would exhibit worse energy efficiency relative to aircraft operating on drop-in fuels, noting that emissions reductions would come from life cycle emissions reductions from the hydrogen. CO2 emissions reductions, high-level observations 2. Regarding the traffic observations, the overall traffic growth rate has an important impact on residual CO2 emissions by 2050 and after. From the operational perspectives, the analysis shows there are opportunities for operations to reduce CO2 emissions through improvements in the performance of flights across all phases of flights, including unconventional measures such as formation flying. On the fuel side, drop-in fuels have the largest impact on residual CO2 emissions, driving overall reductions by 2050, being independent, to some extent, of technology and operation scenarios. Hydrogen is not expected to have a significant contribution by 2050, with only 1.9% of energy share in 2050, but may increase in the 2050s and 2060s if technically feasible and commercially viable. Question 2. Future international aviation emissions in context. Regarding the future international aviation emissions put in the context of the climate science, there are several high-level points. If we consider cumulative residual global anthropogenic CO2 emissions from the start of 2020 to limit global warming to 1.5 degrees Celsius, estimated as 400 gigatons of CO2 at 60% probability, the international aviation share could be around 4.1% to 11.3%. For a warming limit of 2 degrees Celsius, the remaining allowed carbon emissions estimated to be 1,150 gigatons of CO2 at 67% probability, with the international aviation share ranging from 1.4% to 3.9%. Question 3. Cost and investments associated with integrated scenarios. Moving to costs and investments associated with the scenarios, they are largely driven by fuels. Incremental costs of fuels, for example, minimum selling price of SAF compared to conventional jet fuels, further motivates fuel and energy efficiency improvements from aircraft technology and operations. Aircraft technology and operational measures will require investments from governments and industry. Question 4. The impact of aviation traffic forecast. The scenarios described above are based on the mid-traffic forecast. ICAO also assessed the potential impact by high and low traffic forecast. Regarding the traffic forecast and its impact, the table below provides CO2 emissions in 2050 after the implemented emissions reductions from technology, operations, and fuels. As we can see on this slide, after 2050, this uncertainty is growing towards 2070 with an increasing range between high, mid, and low options within the scenarios. The table at the bottom shows the CO2 emissions remaining in 2050 after the implementation of reduction measures. Question 5. Sensitivity analysis of IS-3 scenario demonstrates the importance of fuels. On this slide, we wanted to demonstrate the importance of fuels through a sensitive analysis on IS-3. The diagrams on this slide demonstrate the results of incorporating IS-3 with assumptions from Scenario 1, which is low scenario, and Scenario 2, the medium scenario for technology and operations. These results show that there are multiple paths that may result in similar levels of CO2 emissions, and that the critical contribution from fuels is to decouple the growth in international aviation traffic from its CO2 emissions. Considerations regarding LTAG options. Based on the results of the LTAG-TG feasibility study, technical options for LTAG metrics were identified below. This is not an exhaustive list, and other formulations may of course be considered. One type of options could be using annual levels of emissions in 2050, for example 950, 500, or 200 megatons of CO2. It is also worth noting that using a reference year earlier than 2050 may not give the long-term certainty expected to be a key benefit of adopting an LTAG, and using a reference year after 2070 would be subject to increased uncertainty. Additional intermediate waypoints in milestone years could lay out a trajectory to the emissions profile in time. Another type of options could be using cumulative total emissions. The cumulative total emissions from the international aviation sector by 2050, for example, 23, 17, or 12 gigatons of CO2, depending on the scenario. The cumulative total emissions from the sector would most closely translate into an atmospheric temperature response and allow for monitoring of progress without the need for intermediate waypoints. It is crucial to recall the LTAG analysis was limited to consider in-sector measures only. Out-of-sector measures were not considered in the LTAG study. Impacts of the non-exhaustive list. The analysis also included consideration of other impacts, and this slide provides a non-inclusive list. On the regional impacts, most significant regional variations expected in production and uptake of fuels due to, for example, regional availability of feedstock, renewable energy, and infrastructure. With regard to the impacts on noise and air quality, in all scenarios the traffic growth increase, total noise, and NOx emissions. However, technology improvements typically reduced noise and emissions alongside fuel burn. Additionally, operational improvements may have co-benefits for noise, but did not impact air quality. Another observation is that LTAG SAF and cryogenic hydrogen have co-benefits for local air quality and contrail information with no impact on noise. Roadmaps for LTAG implementation. Moving on to the roadmaps for LTAG implementation, CAPE considered technical aspects of implementation without prejudging future decisions. On monitoring of progress, state action plans may be used for states to report progress towards a goal without duplicating existing processes. If a goal were adopted, ICAO could conduct future work on possible metrics, reporting mechanisms, etc. ICAO may need to review any goal to ensure it remains appropriate. For this purpose, a triennial review process could be considered similar to the CORSIA periodic review, for example. Finally, capacity building and assistance will be crucial. For example, workshops on measures, including understanding costs, assistance on monitoring and measuring of CO2 emissions, an overarching training program similar to ACT CORSIA. LTAG scenario development. With that, I would like to give you the overview of scenario development work. The overall scenario structure. 3 scenarios were developed for in-sector CO2 emissions reduction measures, integrating technology operations and fuels measures. These were termed as integrated scenarios, numbered IS-1, 2, and 3, and color-coded as shown. A baseline or frozen technology scenario was used for reference, which assumes no technology, operations, or fuel improvements after 2018, and this was labeled IS-0. These were overlaid on the COVID-impacted traffic forecasts to give 9 time series for the 3 integrated scenarios. As not stated otherwise, the results that we present in this presentation are provided for the mid-traffic forecasts. The low and high traffic forecasts are also available in the report. The base year of 2018 was used for consistency with the Cape 12 trends analysis, and a time horizon of 2070 was adopted. Summary of LTAG integrated scenarios. 3 integrated scenarios were developed based on narrative descriptions, which you can see on the slide here. As already mentioned, integrated scenario 1 represents the most easily attainable scenario, relying on measures with the highest level of readiness. It is the least ambitious or aspirational. Integrated scenario 3 represents the least attainable scenario with measures currently at a low level of readiness. It represents the top end of ambition. Integrated scenario 2 represents an approximate midpoint between the other 2 scenarios. Composition of LTAG integrated scenarios. Each scenario that I've just described is defined by specific assumptions on the traffic forecast and fleet composition, aircraft technology, operations, infrastructure, and fuels as described in this slide. The technology sub-scenarios were termed T1 to T3, operations O1 to O3, and fuels F1 to F3. Costs and investments associated with integrated scenarios. ICAO used a cost minus baseline approach to assess the costs and investments associated with the 3 integrated scenarios. This means that the costs are incremental costs between an integrated scenario 1, 2, or 3 and the baseline scenario IS-0. ICAO assessed the costs and investments to different stakeholders, including states or government institutions, original equipment manufacturers or fuel suppliers, airports and navigation service providers, and airline operators. For each scenario, the incremental costs or savings from aircraft technology operations and fuels measures were estimated. The cumulative costs from 2020 to 2050 for each stakeholder group are provided on this slide. It's important to note that these should not be added to give total costs for each scenario, as some investments by upstream stakeholders are passed downstream, for example, through price. Key takeaway messages on scenarios. So in summary, integrated scenarios of in-sector measures were developed. These were analyzed to show the impact on international aviation CO2 emissions through to 2070. This slide shows some key results for the mid-traffic forecast in 2050, and we've already seen these presented in a slightly different way a moment ago. Results for 2070 are also provided in the report, but as the uncertainty increases over time, the results for 2070 are significantly more uncertain than those for 2050. It is important to note that all these results vary for the high and low traffic forecasts and attract their own uncertainties as documented in the report, even if they are presented here as single figures. So some key messages we can draw from the results. Integrated Scenario 3 results in the lowest residual in-sector emissions at around 1/3 of the 2019 levels, while Integrated Scenario 1 results in an increase of around 60% in in-sector emissions by 2050. A residual in this case means the emissions after in-sector measures have been applied. Compared to doing nothing, up to a reduction of around 90% in in-sector emissions is technically feasible by 2050 compared to the IS0 baseline scenario. In most cases, fuels have the largest contribution to the emissions reductions, followed by technology and with operations contributing the least. The annual reduction in energy use per revenue ton kilometer compared to 2019 falls between around 1 and 2% in all scenarios. And finally, as was presented a little earlier, cumulative emissions over the analysis period are also included in the report, and these were used by ICAO for comparison with the global allowed emissions data from IPCC. LTAG technology. Now we will describe the work related to the LTAG technology aspects. LTAG technology. Studies of the type LTAG have a lot of assumptions, so it's imperative that a very thorough investigation is performed so the confidence is high and the scientific process is actually obeyed. We tried it in every step to do it in the most thorough way possible. Just to give you an insight of how the study was performed, there was a series of stock-taking events, and of course we reviewed the variety of different ICAO documents. Plus, we reached out to various research organizations from around the world to find out what ideas, technologies, concepts they're working on, and then those concepts were binned into airframe improvements, propulsion improvements, energy and energy storage improvements, and of course, any type of advanced concept that might be looked upon in the future, and some of those examples are in the charts here with the next slide. Aircraft under consideration. To make it a little bit more visual, the ICAO aircraft categories are numerous and using it would have taken an enormous amount of time. So it was decided early on that probably the best way to do it is to identify proxy aircraft in the areas where most of the operations and most of the fuel consumption was occurring. In this case, you will see there are 5 different vehicle categories that were selected and the representative vehicles where data were obtained. Then, all the analysis was calibrated against them to make sure that any type of improvement is actually justifiable. And then on the right-hand side, you see the various different configurations that have been introduced or suggested by different entities. We try to be as agnostic as possible as to which vehicle we are recommending, and we tried to create an average of the types of improvements that these vehicles can achieve in the future. Integrated technology modeling process. So in terms of the process, we started with these vehicles, and also we started with the various technologies that people were suggesting. And of course, since we're trying to do this in a quantitative way, the tools must now speak the same language. All this information must be translated to the information that the analysis can understand. That is where the about 100 different subject matter experts on the technology side from around the world came together to help us translate these improvements, and not only for one point in time, but over the following 3 decades, and also trying to bracket these assumptions based on different scenarios around these technologies. Then that process was repeated for each and every one of those vehicles. And then, in the cases where the fuel was not a drop-in fuel, we tried to see what implications that would have into the design. Then we looked at the operations of these vehicles and the aircraft retirements, because part of our assignment was to also figure out what would be the market penetration of those vehicles. Then all this information was tabulated and sent for modeling and propagated, all the way to the fleet analysis and the wedge charts that you are accustomed to seeing. So this information was necessary in order for the analysis to proceed. Narrow-body ATW technology identification. So just to give you an example, we are picking up here the narrow-body advanced tube and wing technology against the A320 class vehicle. The examples for dynamic structures and propulsion are indicating the types of things that people are advocating, and it's those words that then get translated into inputs into the analysis. Narrow-body potential entry into service, EIS. So after the analysis is done, we're trying to figure out what classes of vehicles we're pursuing. This is where the scenario work is coming in. The orange scenario, the T1 advanced tube and wing ATW, is the traditional evolutionary way that studies have been done in the past, or how things are progressing over the next 2 decades. And then in the green T2 scenario, you have advanced configurations, but limited infrastructural changes, so it's a little bit more doable. And then the blue scenario, T3, is the one where all of a sudden we're removing the constraints of infrastructure. We're trying to determine what ideas are available, determine if those ideas have any benefit, and if then quantify what are the technical barriers and what type of regulatory or infrastructure implications those might have. Vehicle perspective, narrow body energy trend. This is showing the energy intensity of the vehicle, and the T1 scenario is at the top with the orange color, and it's also indicating the uncertainty in those estimates in terms of confidence. Then the green one indicates the T2 scenario, and the blue one indicates the T3 scenario, and that was done all the way to 2050, and the comment was made earlier that we took this assessment right up to 2070. The reason for that is that by the time we are introducing something in 2050, there is such a small number of vehicles in the fleet that obviously it doesn't have a big implication in the overall picture. So you almost have to let it run for another 10 to 20 years to really see the impact of the investments that we make. Key takeaway messages on technology. So in summary, we see that the conventional tube and wing aircraft still continue to make improvements, but by themselves they won't be able to get us there. So we start looking at advanced configurations linked, of course, with fuels that will be discussed next. And then in the end, we try to tabulate for each and every one of those classes the percent improvements expected. And that was an integral part of the input that leads into the fleet propagation. LTAG, operations. Now we will summarize the work that has been done on the operations side. Operations categorization. The operations-related task was to identify and evaluate existing, already foreseen, and innovative in-sector measures in the area of operations that could potentially contribute to the reducing of CO2 emissions from international civil aviation. There are actually three parts of the task: the data collection, the operations categorization, and the formation of options of scenarios for the operations. For the operations categorization, the analysis was based on ICAO CAPE work on airports and operations, and specifically on the results that already obtained from the environmental assessment of the Global Air Navigation Plan, GAMP, and the measures in its aviation systems block upgrades, ASBU. A baseline was provided on a large number of identified operational measures from that assessment, and the expected fuel and CO2 savings of those measures, and the data analysis revealed that there were a number of operational measures additional to those that were previously assessed by ICAO CAPE. Next to horizontal and vertical flight efficiency, which were part of that previous list of measures, there were three new inefficiencies added, and they were used to adjust the baseline that was previously established by ICAO CAPE. These new measures you can see here in the list. They were ground operations inefficiency, innovative flight inefficiency, and advanced flight inefficiency. With respect to the ground operations inefficiency, you can think about typical infrastructure-related measures such as taxibot. Innovative flight inefficiency are operational measures implemented as of 2038, for example, formation flying. Advanced flight efficiency refers to the introduction of, for example, advanced concept aircraft in the fleet, such as a blended wing body we've seen in the previous presentation, which could introduce different performance characteristics and consequently impact the overall flight efficiency, which could work in two ways because it could work in a positive direction, allowing more capacity or negative impact due to a larger heterogeneity of the fleet. Operations scenario definition. Similar to the technology, you see here the scenarios that were developed. A baseline and three scenarios relative to this baseline were identified, and these operational scenarios were then to be integrated with the other scenarios for tech and fuels. The baseline was integrated with the integrated scenarios IS0. It assumes that no further improvements after 2025 were to be implemented with respect to the operations. The three scenarios O1, O2, and O3 that you see here in this slide represent an implementation of measures with a decreasing readiness and attainability, but with an increasing level of aspiration, meaning more CO2 reductions. Scenario 1 represents lower conservative end of the range of potential greenhouse gas reductions from operations, and in this scenario there's a low rate of the earlier mentioned ASBU elements deployment to optimize horizontal, vertical, and ground operations efficiency. The operations scenario 2 represents the middle of the range of potential greenhouse gas reductions from operations, and in this scenario there is a medium rate of ASBU element deployment to optimize the horizontal, vertical, and ground operations efficiency, and a low rate of operational measures deployment to optimize the innovative flight efficiency and advanced flight efficiency. And the operations scenario 2 goes a step further. Here we see the medium rate of operational measure deployment to optimize innovative flight efficiency and advanced flight efficiency on top of the optimization of the other measures. Summary of fuel efficiency improvements from operations. This slide summarizes the fuel efficiency that results from the various options. In this summary, you see a relative contribution in percentage of the fuel efficiency improvement based on the operational measures into three integrated scenarios that have been presented before. It clearly shows that there is quite a difference between these three operational integrated scenarios with respect to the contribution that operations could give, and the upper, mid, and lower line for each scenario corresponds to the aviation traffic forecast, low, medium, and high. After 2050, I repeat that again, the uncertainty grows obviously towards 2070 with an increasing range between high, mid, and low options within these scenarios. Key takeaway messages on operations. This slide summarizes the key takeaways. There are three scenarios defined for operations to represent increasing levels of ambition that are aligned with technology and fuels. The analysis shows that there are opportunities for operations to reduce CO2 emissions through improvements in the performance of flights across all phases, including unconventional measures such as formation flying. A summary of the percentages of the fuel efficiency are in the table below. LTAG fuels. Now we will talk about the work of the LTAG fuels component. The LTAG fuels approach. The way that we approached the work of the fuel assessment was to go through and first categorize the types of fuels that we would consider. We did this for both drop-in fuels that can be used on today's aircraft, as well as non-drop-in fuels that would require new air vehicles. And we then went through and looked at the scenario definitions that you've heard about thus far. We developed scenarios for fuels that are in line with those presented by my colleagues, and thus consider the expectation of not just the development of aviation, but other sectors as well, with a careful consideration of the readiness and attainability. We then did analyses of the different types of fuels, each of these categories, to understand what the production potential could be, what the potential life cycle greenhouse gas reductions could be, as well as economic and infrastructure issues associated with fuel production. We then developed scenarios that were not constrained in any way. We just looked at the amount of fuel available and then summed that fuel, and we compared these to the demand that came from the ATAG Waypoint 2050 analysis, and in many of these scenarios, the volume of fuel exceeded the demand from international aviation. In the end, we constrained the scenarios. We don't need to produce more fuel than is needed. So then we looked at how to select fuels, and I will talk about that in a little bit. There was an iterative process here with the technology work to tell us which certain types of fuels would be needed, and then we would iterate back and forth with them to come to the final analysis. Fuel categorization. So in terms of the fuels, as I noted, we considered two broad categories of fuels: drop-in fuels, in other words, fuels that could be used with today's fleet of aircraft, as well as our existing pipeline and airport infrastructure. From that perspective, we looked at sustainable aviation fuels produced from biomass, from solid and liquid waste, from gaseous waste such as carbon monoxide and carbon dioxide, as well as sustainable aviation fuels produced from atmospheric CO2. We also examined lower carbon aviation fuels, that is, petroleum-based fuels that would have at least a 10% reduction in life cycle emissions. We also looked at non-drop-in fuels. We did an examination of electricity, realized that that's not really applicable for this purpose, as we're looking at international aviation, and electrically powered aircraft have a relatively short range. We also looked at liquefied gas aviation fuel. However, these would be using stranded resources and also would not be applicable for international aviation. And finally, we did a detailed consideration of cryogenic hydrogen, looking at a variety of low-carbon sources. And so we ended up doing a careful examination of the sustainable aviation fuel, the lower carbon aviation fuel, and the cryogenic hydrogen. Fuel scenario definitions. In terms of our analysis, as I mentioned, we had the three scenarios. We aligned these with the work being done by the other LTAG components, and within each of the three scenarios, we emphasized a different aspect. So in the fuel scenario 1, which aligns with IS1, we emphasized low cost. So we selected fuels based on their minimum selling price, and this reflects a scenario where alternative fuels are approved at greater than a 50% blend. Ground transport and aviation have a level playing field with respect to alternative fuel use, and this means that ground transport is still using a lot of liquid fuels, and there are relatively low incentives for the production of sustainable aviation fuel, lower carbon aviation fuel, and as a result, we're using some waste gases and some feedstocks that are not being used today. Under fuel scenario 2, based on the combination of cost and greenhouse gas savings, and we computed this using the marginal abatement cost. We computed the cost per CO2 avoided for the various fuels that we're looking at, and that's how we chose which fuels to use, because our SAF production exceeded our jet fuel demand under this scenario. Under this scenario, we assume that ASTM International has approved the use of 100% synthetic jet fuel or 100% sustainable aviation fuel. We're assuming that there's considerable electrification of ground transportation, and therefore there's a lot more feedstock available to produce SAF. We have increased incentives for SAF production and LCAF and production, and we have widespread use of waste gases for SAF fuel production. In the fuel scenario 3, to go with IS3, this is where we get to our maximum greenhouse gas reductions. So in addition to SAF and LCAF, we have non-drop-in fuels, and in this case, we're selecting fuels based on which ones provide the maximum CO2 reductions. And under this scenario, we're assuming economy-wide deep decarbonization, extensive electrification of ground transport, and widespread availability of low-carbon energy. Leading to this, we have large incentives to get to low greenhouse gas fuels for aviation, and we're using atmospheric CO2 to produce SAF. And we have multiple types of SAF that could potentially exceed jet fuel demand. But there's also sufficient hydrogen available to enable the use of cryogenic hydrogen in aircraft, and the investments have been made to make cryogenic hydrogen available to all the airports as well, so considerable investments. Scenario F1 IS1, F2 IS2, F3 IS3, mid-traffic forecast. So the graphs here show for the mid-traffic forecast the types of fuel that would be in use from now to 2070. Gray is conventional jet fuel. The dark blue is lower carbon aviation fuel. Light green is sustainable aviation fuel produced from biomass and solid liquid waste. And the dark green is sustainable aviation fuel made from waste CO2. As you can see under F1, there's some LCAF being made and growing amounts of SAF being made, but there's still considerable amounts of conventional jet fuel. Under scenario F2, the conventional jet fuel stops being used in 2050. There's a considerable amount of LCAF being used, but many more volumes of SAF from biomass and solid liquid waste, as well as SAF from waste CO2. And I would note under this scenario that there's additional SAF that could be produced. Under scenario F3, conventional jet fuels are not being used after 2040. LCAF is not being used after 2045. We have SAF being produced from atmospheric CO2. You can see that this is the yellowish color. And then cryogenic hydrogen available after 2050. That is the blue color. Again, more SAF is being produced as shown here, but other fuels were selected for their lower CO2 footprint. Key takeaway messages on fuel. In summary, we developed 3 scenarios to represent increasing levels of ambition, and these were aligned with technology and operations. The LTAG SAF volumes exceed demand under 2 of the 3 scenarios. The table in the lower right shows the reductions in life cycle greenhouse gas emissions for the middle traffic forecast. And as you can see in 2050, depending on the scenario, fuels could provide between a 20% and 80% reduction in the life cycle greenhouse gas emissions from international aviation, and under the most ambitious scenario in 2070 could be close to providing a 90% reduction. Main takeaway from the LTAG report. This is the last slide we would wish to share with you. It is summing up everything to a certain degree, the main takeaways from the LTAG report. Within all this impressive work, what are the main takeaways there? So if you look at all the scenarios with all the variation, they show a substantial potential for CO2 reduction. However, you see that none of them reaches zero CO2 emissions using in-sector emissions only. So as was mentioned, also in the introduction, we only looked into in-sector measures, so out-of-section measures were not considered. There will be residual emissions despite 100% replacement of conventional jet fuel with novel due to considerations of fuel's life cycle emissions. The sustainable aviation fuels don't come at zero CO2 impact if you do a thorough analysis of their life cycle emissions. When it comes to the airplanes, we can see that advanced tube and wing aircraft have a clear potential to improve the fuel energy efficiency of the international aviation system with some incremental contribution from aircraft with unconventional configurations, which will enter service also only later in the time frame we have looked into. On operations, there are certainly opportunities for operations to reduce CO2 emissions through improvements in the performance of flights across all phases of flights, including also unconventional measures such as formation flying, but their contribution certainly is not among the biggest elements. So drop-in fuels have the largest impacts on residual CO2 emissions, driving the overall reductions by 2050. I think that's very important to note that at least part of the silver bullet lies in the drop-in fuels, and I shouldn't stop without mentioning that hydrogen is not expected to have a significant contribution by 2050, but may increase in the 2050s and 2060s if it is technically feasible and commercially viable. So, in summary, I'll bring you to the last elements here that are the most aggressive scenario. In 2050, there will still be around 200 megatons of CO2 emissions in 2050, 35% of what we had in 2019. A reduction in 2050 from the baseline, which could be achieved under this most aggressive scenario, is 87%. But if we don't do much, in the lowest scenario, we only reach approximately 40% reduction. And the cumulative residual emissions from 2070 out to 2050 here are in an order of magnitude of between 20 gigatons of CO2 under the most aggressive scenario down to plus or minus double of that amount, 23 gigatons of CO2 in the lowest scenario, IS1. With that, we finish this presentation. Thank you very much for your attention.